Well, good morning, everyone. Happy New Year. This is Jim Chastain with EasyPower, and welcome to the 2016 Refresher Series. We hold this session every Tuesday morning with brief tips and techniques on using the tools for certain applications as we've had requests in over time. So today's refresher session is a brief overview of the powerful display features of the coordination module, PowerProtector. And we're going to focus on how coordination can be accomplished with any of the different MCC modeling options in EasyPower. Frequently, protective devices will be installed upstream in the switchboard area or even in standalone switchgear from downstream loads that potentially may be susceptible to faults or controlled within a motor control center. To properly protect these devices, the coordination module must display performance curves for these elements wherever they reside in the system. So we want to identify fault currents, both arcing and bolted fault currents in the TCC plots, and see which protective devices is activated for any of these types of loads. And then be able to compare how long it takes for one specific protective device with any other device in the system. Now, EasyPower offers multiple ways to model MCC panels or systems. In other webinars, we've actually discussed these different ways. The different projects that you address may benefit from one modeling method to another, and ultimately you're the one that needs to make the decision on which method to use. So an MCC can be modeled as a single bus icon where everything's contained in the MCC. It can be modeled as separate loads where each bus is represented physically in the system and then each load is represented, or can be a combination of these two modes. So now there's trade-offs involved, and one of the biggest reasons that people would choose the first option is to limit the number of buses they have to deal with in their system. So real briefly, let me kind of take 2 minutes and show how this is done. So I'm going to jump into the tools. What we have here is this is actually a sample database that's in the samples folder when you install the tools, but it's a fairly complex system, and the reason we show that it's quite literally optimized for the utilization of MCC icons. So what you see here is multiple utility sources, multiple cogen opportunities or situations, and then a large number of MCC panels down here at the bottom. The point that I want to make is as I go to the database browser and we look at the basic content of this file, this is literally a 50 node or a 50 bus design. And significant in that list of buses is a number of MCC schedules that we're using. You'll see here we've designated 7 as their total MCCs, and so as I call these up on the database display, we'll just pick one out. And you'll see that in each one of these we have between 20 and 30 loads, all detailed, and most of them are motors. Now if we want to, for instance, model or coordinate against the largest load in this MCC, we would, let's say it's, for instance, this 150 horsepower motor here, rather than designate it as a straight motor and the load type, we would select from the pull down option a motor with TCC. And you can see we can utilize both motors, VFD controlled motors and linear loads with TCC plots. In this case, we'll choose the motor load with TCC. And as we do that, the size of the motor was grayed out over here on the right. So as I slide over Now we have, in fact, the whole description of the motor has been grayed out. We utilize this data dialog entry, and we treat this motor now as any other standalone motor. So this was a 150 horsepower motor. We can calculate the full load current. We calculate the X over R for that motor. And then the MCC will be plotted, and we can plot the thermal limit curve and make adjustments to the lock rotor multipliers for starting current as we would with any other motor. Now as we've done that, then we would come over here to our protective device, and we see that it's set up as a fuse. Well, clearly we want to be able to make some adjustments, so we're going to choose a low voltage power circuit breaker. And now as we do that, rather than enter the device information as we would in a standalone fuse, we would again use the data dialog button to pull up the low voltage breaker data, and we would treat this just like we would a standalone breaker and be able to pick up any breaker that has a TCC or has any trip curve involved. And there, for instance, in this particular case, we might pick a 400 amp plug, verify that it's in the database, and then this would be the trip settings that would be plotted on the TCC. So all that's involved. In fact, that's primarily what's involved in setting up the TCC, to utilize the TCC in the motor control center. Okay, the benefit then is, rather than just have the 50 buses that we're dealing with, we have quite literally over 200 buses now, or 200 loads that are included in this design, and we haven't used anything more than a 50 bus limit on the whole system. Consequently, the tool requirement's smaller. Okay, so that's what I wanted to cover there. Let's jump back into where we're going. Now, the function of coordination, which is what we're going to really focus on, is the need to isolate downstream loads as much as possible close to the load that's at fault, and thereby prevent the loss of power to other loads. So there's one thing to consider when we're doing this, and the problem is the process of coordination actually can exacerbate the arc flash incident energy calculations either at the load or upstream at some of the intermediate protective devices. And so this can often interfere or compete with the settings which we might want to choose for coordination. The EasyPower PowerProtector module is the tool that permits the visual display of the performance curves. Some of the features that are built into it are the drag and adjust features that show what the performance and time differences would be as we make adjustments to the trip settings on a device. We can also show the time delta between devices, whether they're in the MCC control center or not. One of the features that people like, especially because it's not available in any other tool on the market, is that EasyPower recalculates incident energy and arcing currents as we make adjustments both upstream and downstream, and so you can see at the time whether you're going to end up with the result that you were hoping for or not. And again, this works anywhere, even including an MCC, as long as we've designated the load to have a TCC display. Now, as we kind of get into this, what I want to show is basically these three methodologies and then compare them on the essentially equivalent circuits. All right, so here's another one-line diagram. On the left, we here have an example where we have included literally all the loads inside the MCC. And so here the reason for this is to optimize the number of buses we're using in our system. So we could put as many as 20 or 25 or 30 loads in the MCC if that's what our system set up. In the center, I have a discrete or separate devices comparison, whereas this would be bus 1 would be effectively the main MCC bus, and the breakers and downstream loads are comparable to what I set up in the icon. And then the third illustration is a combination where we've outboarded a high load or one of the largest loads from the MCC, and I'll go into the reasons why we do that and what benefits it gives us. So first I want to go to short circuit focus, and I want to look at my options, and under the arc flash hazard tab I want to verify that as I'm calculating worst case arc flash hazards, I'm utilizing the main breaker for the bus that we're looking at. Likewise, I also have no limitations on the amount of time that we're doing the calculations. I prefer to do this as a first pass to make sure I'm really looking at what the calculated arc times are, no matter where it's going to end up in the system. There's no artificial limitation on the incident energy. Then I go to coordination module, left click and highlight, and we're going to pick out the MCC panel, the upstream breaker, feeder breaker, and then the upstream main breaker on the switch gear that's feeding that MCC, and we're going to plot the time current curve. And so what we see here now is a display that shows us, first of all, I'm going to pull down my motor starting curve. So this is the 250 horsepower motor that's within the MCC. In this case, it's coming off of row 2 or bucket 2. And this curve is plotted based upon the parameters that were in the setup box, the locked rotor multipliers and inrush that we were controlling as we set up the motor parameters. This next line is the breaker performance curve for row 2, which is the immediate breaker upstream of the motor. Then this is the main breaker on the MCC. Here's BL1B, which is my feeder upstream of the MCC. And then finally the switchgear main that's upstream of the breaker that's feeding the MCC. So you can see at first pass, these looks like they're coordinated as far as what I'm trying to do. The point that I'd like to make is that as we highlight the MCC and we fault that particular bus, the tools show us what the arc current or what the bolted fault current is coming down from the utility, and we see that there's a total, at least for a momentary fault, of 21,670 amps, which means that there's a fair amount of motor contribution from downstream loads in the MCC, because we're looking at the main bus in the MCC as far as its total current. Now, one point I want to make here is if we want to look at the trip settings, the current, this particular current is not going through the row 2 breaker, because this again is on the main bus, it's not on the load. So for purposes of coordination, this looks like things are set up pretty well, but in reality I don't have any way to verify if the fault was at the motor. I don't have any way to verify specifically what that fault current is and whether or not it's going to give me a coordinated system. So for the purposes of this discussion, I'm going to remove this breaker from my plot because it's the row 2 breaker, and the current that we're currently looking at doesn't go through it. So I'm going to select that curve and remove it from my display. This brings me back to now, as I select this breaker and I want to insert my arcing tick mark. In fact, I don't do this on purpose, but as I do this, it's telling me I can't display the arcing current for this device. The problem is that we can only have one breaker or one bus fault when we're doing that display. So I want to make sure I isolate that. And as we've got our settings set up, we can see that we have incident energy for the main bus on the MCC is well within the civilized area, and so for purposes of coordination, the display shows that the main panel, or at least the main breaker, oh, I took off the wrong one here. So row 2 is the one that I mean to eliminate. Let's come back here and look at the current. As I fault it, I should be able to display what my arcing current is on the main panel. All right. So what I'm seeing here is that we have, for bolted fault current, these displays are due to the setup parameters of the breaker that we have in the main breaker for MCC1. And as we set up the short circuit, we're using momentary current for both the tick mark, which is this 22,876 amp mark, and for TCC clipping. As I remove that, you can see that the display then goes out beyond the end of the tick mark. And so we frequently want to be able to use the tick mark to clean up the display. All right, so in terms of coordination, this looks like we're in pretty good shape. In terms of incident energy, the main bus looks pretty good. If we fault all the buses, you can see that we may have a problem with switchgear 1, but we're not too worried about MCC, the main bus in the MCC. So we would normally save this particular plot, but in this case it's not. We want to go to the standalone or the separate icons and go through the same process. In this case, though, we should be able to see what the current is on all the way to the load. And that's because we've got a separate bus now between the motor that potentially could be at fault and the switchgear or the trip devices within inside the MCC. So back on my one-line diagram, you can see that we have M8, which is the secondary motor that we don't necessarily want to be concerned with. So we're going to take that out of the picture. Here's M1, which is the motor we want to coordinate against. Here's the main on the MCC. Here's row 2. Again, the BLC1, which is my feeder, and then BL1A, which is the upstream main. Now we can fault this bus. We can plot the arcing current, and here you can see that if I move this up and down, that this is the arcing current that's going through the motor if that's where the fault is, and it's calculated to be 8,552 amps. And so very clearly we can see now in this case, this breaker, which is right immediately upstream of the motor, will trip first. Next to trip will be the main breaker on the MCC and the upstream feeder. So the next thing we want to do is to be able to calculate the difference between these trip times. So I select the lower curve, hold down Shift and select the upper curve, and create a difference by clicking on the difference calculator button. And now as I locate that particular difference calculator over my arcing current, I see that I have a separation of almost 0.2 of a second. Likewise, I want to verify coordination with the next breaker upstream. Select both. There's my tripping current, or my difference calculator, and then we'll do it a third time. And for purposes of the arcing fault, these will be, we have 185 milliseconds, 50 milliseconds, and then 13 seconds separation between each of the breakers in the system if we have a fault at the remote motor for the motor leg. However, if we go in and look at the arc flash calculations, the individual bus or the connection with the motor looks fairly civilized, but if I fault all the buses, now you can see that our bus 1 in this case, which correlates to the MCC main, has a relatively high incident energy compared to what it was when we were considering it as the basis for the fault. And so now we have a decision to make whether or not we can coordinate against this particular motor and sacrifice the incident energy if we need people to work on the main bus of the MCC. Now, if we look at this, we can see that the main breaker on the MCC is what's driving that incident energy calculation, and that's in effect the result of where this trip setting is for this upstream breaker. As we make adjustments to this breaker, you can see it brings down the TC, or the incident energy calculated for the main. But now again, we've kind of violated our coordination, and so we need to decide whether or not that's something we need to deal with, or consider this as maybe a procedural step in terms of making an adjustment. If we need to work on this hot bus, making an adjustment of the trip setting to now these new settings, and then restore them once we go back to normal operation. Again, that's procedural discussion that you'd want to have within the group. All right. Again, I'd save this if I were going through this study. And now we want to go to the third possibility, which is a combination of these two modeling techniques, where I've got all of my other loads inside the MCC and I've outboarded one single load because that's where I want to pay attention to for my mitigation and coordination. So again, we highlight those downstream breakers, plot this curve, and you'll see we have very much the same type of display. Here's our row 2 bus, which now resides inside of the MCC. Here's our motor that we're coordinating against. Here's the main breaker on the MCC panel. Here's the first upstream breaker, and then the main breaker on the switchgear. Again, now here we can coordinate to this particular load because we have a bus separate from the MCC. So as we fault that single bus, we can insert the arcing current, and you can see we have pretty much the same results, the same current within a couple amps of predicted fault current for that motor. Now that it's outboarded, and we have the same problem in terms of coordinating and mitigation for the main energy on the MCC. When I go in and look at the energy, we have a civil incident energy for the connection point between the motor and the cable or downstream load. But if I fault all the buses and look at my incident energy, you can see now we have a high incident energy for our MCC, and again, this is due to the fact that the MCC1 or main breaker is set so that it would coordinate with what we're showing for the downstream load. And again, we can make an adjustment there and see how it improves the incident energy calculations on the MCC. But again, we go back to the point of violating the coordination that we look for. Now, likewise, we can still do the difference calculations. Now here, we're calculating, I guess I want to go back and look at my faulting current. And as we center our faulting current over the arcing current, we can align and calculate all the differentials between each of the breakers. And in this case, they're in different parts of the system. And here we're looking at the main switchgear bus, separation between the main switchgear and the downstream feeder, and then between the downstream feeder and the main on the MCC, and then between the main on the MCC and the row 2 control, which is the disconnect for the motor itself. And so we end up with similar results, some minor differences due to the fact that these are frankly estimates and they lack a certain amount of precision just based upon the IEEE models. But I think this demonstrates where I was trying to go with our discussion. So the 3 different methodologies for doing MCC modeling, each of which can be, we can utilize our power protection for coordination and the different trade-offs involved. So as a real quick review, what we learned is the fact that the curves will be plotted for any device that has a TC curve within the one-line diagram, and we can pick these up even across transformers and across different bus systems. For instance, if we wanted to include a relay at the top of the distribution system, we could just as easily include that if we wanted for some reason to coordinate it against the downstream loads. Okay, we're also showing that if the arc flash incident energy calculations are required, then the load must be separated. Or just wanted to mention that we do have regional training, some new locations now announced on the website. If you have tool-related questions, you're more than welcome to contact tech support at easypower.com. If you'd like some backup or some expertise in reviewing the work, if you're doing a first study or some aspect of coordination that you haven't done before, you're more than welcome to request a quote for an engineering review of your files. I appreciate everyone attending. Again, if you have other questions, you're more than welcome to contact me or tech support at easypower.com. And I appreciate the chance to talk to everyone, and we will talk to you again next week. Have a good day.